video, the one I just put out, called FIU Bridge Collapse NTSB Report Debunked Tide Arch Bridge. Why bridge failed simply explained. Simply explained. What made me think of that is I'm trying to refine it. You know, these videos, you see them, how my format is. Mark stated here, the first thing that I noticed is that the investigation involved, whatever he states, right? You can read his comments there. I want to jump to my reply because Mark makes me realize that he's still going back to the hinging. Remember, when I get data, if it doesn't, it has to go in. If it doesn't work in my previous load path failure design or analysis, then I trash it and I have to make it work. So all the cracks have to work. In this case, the cracks and statements, not all statements have to work. Some of them you can discount. But in this case, we have this crack, and this is elevation. We talked about that elevation before, but I did not have the data of the true crack, that it took place. Oh, okay, where are you? That it took place on 2/8. This is a 2/8 crack. This was before they transported it, before it was even on the transporters. So this crack is presented while the post-tensioning is still in place. So I'm going to try to do this chronologically so you guys can follow. This is 12, and that's the 11 behind us, or in front of 12. This is the diaphragm. That's the part it all interacts with. This deck was done first. This upper 12 was done secondarily. Keep in mind at the bottom of 12 that hangs off the back of this diaphragm was actually poured at the same time as the deck. This 12 is poured secondarily from that. After that, conceding after that, and it's tied in with rebar reinforcement from the lower deck into this, tying them together, reinforcement as you saw in the OSHA reports. Oh, wrong one. Let me pause this and find it. I thought I was going to click to the right window. Correct window. Hold on. So as you see, this is the OSHA report we're looking at here. This section here is what I'm talking about. This was all poured as one. This lower part, including this little bump out, was part of the deck. The diaphragm pour along with the deck. Diaphragm is where all these meet. All these post-tension members meet. This is the drain pipe. Internal inside here is the post-tensioning bar B, I call it. A is the lower one. The lower one, is in the deck itself. It does not go out here inside into the back of 12. It stays embedded in the deck. So the forces, I'm going to jump around and then come back to it chronologically, but I want you to know that the forces in here are about 300,000+ pounds of force. So imagine it's a rubber band, and you could put 300,000 pounds of force. And when you release one end of the rubber band, it's going to have 300,000 pounds of force to deal with. So this was already crumbled. We already know it was already broken and fallen off. Yet they still loaded it with 300,000+ pounds of force. And it brittlely fractured. It just abruptly, ultimately failed instantly. Once it did that, it no longer had I guess I have to tie it into the previous video. It no longer would act as a tied arch. This connection, and I'm going to show you tied arch in a moment. I should have sort of added that first. I guess I'm going to refine this in probably the following video, but this one I'm going to jump around and we'll get it cleaned up by the time I do a presentation with my model that I'm going to make. So the force, once it destroys this connection, that 12 breaks through here, it no longer has the ability to hold 12 down in any capacity. That allows it totally to be free, this part here to be free, to be able to sag with the deck. The post-tensioning in number 11 is in the deck. It's internal. So it's acting as still a tie, if you will. It's still acting as a tie. It's still got some anchoring back there, albeit limited. It now lost the ability to keep 12 connected to the deck, to stay on the deck. Recall this, though, that I said that the post-tension goes through 11 and stays in the bottom of 12. It never really connects 12. This is 12. It never really connects 12. The post-tensioning bar dissects it just by a clip, just a little bit right there in the bottom of 12. 12 is about 2 foot deep. Just right there. Nothing really there. The clamp force is still in the diaphragm. So you could almost remove this in your mind. Remove this. And now you just see that you have this only. I'd like to think about how to do that for you. So you have this only keeping all this integral system together. Denny Pate, Linda Fig, they state that this is a compressive, everything's supposed to be in compression. Nothing is supposed to be in tension, so everything's crushing together, if you will. Everything has a load on it, compressing. This is what keeps this deck from sagging, is that, I'll use the same analogy I did in the previous video. You grab a rubber band, and you have a loose rubber band. You put a penny on top of it. It sags. Now you put 50 cents on top of it. It sags more. But if you were to pull that rubber band apart from each other, left and right hand pulling apart, you can now support the weight of the 50 pennies on that rubber band, and you can keep it taut, or you can have it a little bit slack and it sags. Well, you can imagine that if you can't have this sagging because it's all concrete integral to each other. And so if it were to sag, you'll start getting crushing moments and things crushing and not working well with each other. So I talked about in the previous video. So we can't have this sagging, and this is what stops them from sagging. These are the rubber bands all pulled tight. All 6 of them pulled tight here and here. So the deck theoretically can take, as Denny Pate stated, it's a redundant system. The deck can take the load of the entire system, which is what it was intent, apparently, but if it's sagging, it's not taking that load. So that means the post-tensioning, if it's sagging, is not doing what you designed it to do. That it's sagging for a reason, that it can't exceeds the rubber band's ability. All right, let me pause this and keep going. So talking about the cracks like hell, this is the crack like hell. But remember, I show in the video, the images presented by, after the NTSB report presents a fine crack there. That fine crack is exactly where this pipe is and coming across here. It never cracked like hell. It was already cracked like hell when it was in the staging area before they moved the structure. A hairline crack is the same as a full crack. If I were to put a hairline crack in here, it is a full crack. But we'll explain more about that in a minute. So from the OSHA report, you see that this is a top view of the crack. And the significance of this is that this is the diaphragm, and this is also the concrete, interacting together, the concrete of the 12. Remember, 12 is sitting on top of the diaphragm, and yet there's no separation from here. They state that it pushed this off, that it was able to push it off. But I state that clearly doesn't make sense. If it pushed it off, why did it raise up in the air? It's raised up in the air because of sagging. It's elevated. This is not pushed off. You push something off, it falls down, right? How come this is pushed off and it goes up in the air? It's been detensioned, so I can't add that, well, some of the tension pulled it up from the post-tensioning in number 11. No, that it's been detensioned at this time. So these are acting together, and it broke off together. They're pushing, again, they're sliding off. This crack, though, the significance of this is they base it on detensioning. This crack, well, they actually don't talk about this crack too much upon detensioning about it. But they actually do. They say it slides, it does pushing and all this. It can't do any of those unless the deck is sagging. So we have this part here that's of interest. The deck is sagging. It's also leaning away. So it's up and away towards us. Let's be clear about that. So it's up and it's cantilevering it down. That's why we have, let me try to do this. It's cantilevering it over. So if you were to grab, and I did this in other videos, if you were to be able to grab the top of 12 and push it towards number 1, that's the far end of the structure, you'd get an opening here. And this is what this is an opening crack. You'd also explain all these cracks, why this one is more forward to us than this one is, all the way up to here. It explains that, and you get that by a dip in the deck, because you couldn't just push 12 over towards 1, and that would cause a racking issue. The whole thing would have to rack. That's not what I'm saying. But if you get the deck sagging towards the center of the structure, you get to explain both ends of the cracks, both ends of the structure, and more specifically this end, which is the failed end. And why is it the failed end? It's a different design than the other end, and totally different design. They both would have experienced it equally had they been designed equally, but this is the weaker end for quite a few reasons I explained in many other videos, post-tensioning, etc. This again is up, 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 and a rotation is taking place. I talk about that because you can see the depth change. They have this sliding down, it's pushing away and down, but clearly this is an inward motion. This is not away and down. This is inside, internal to this. And that's what's amazing. How did it get that internal rotation? And there would be an interesting void it filled. Once it rotated inwards, the question would be, what happened to this post-tensioning? Did it become more? Did it become slack? How much slack did that result in? This is one of the time shots of it. I talk about this here in one video, calling this structures out of equilibrium. That when they detensioned it, it shouldn't have any rotation. But the structure is not balanced left and right, north or west and east, however you like to look at it. So this caused that rotation. That's why we see a higher measurement there than the other side. The rebar reinforcement I talk about, this is the photograph of it, going to prove the elevation difference. This one here is so critical to what I'm talking about. This shows this elevated up in the air, and yet it weighs about 10,000 pounds, and yet it went up in the air, and they have it pushing away. It went up, and it created and here's your gap. So it's up and leaning back towards us. Well, it's hinging, but the post-tensioning bars are inside here still. They regripped as I theorize, and you can see the angle of it. This is kind of down. This is more of a higher piece here. This piece obviously stayed a little more integral to this lower piece here, and we can ignore those for now. I've talked about them so much that we don't do that. This explains the cracking, the cracking, the twisting effect. This is after detensioning. So this is before they put all that tension back on it. Remember, their theory is this fractured member can push off 12. But yet we see in the report, they use when they try to do their reenactment of this, Denny Pate's expert engineering and forensic people, no less, they're so stupid that they use not this type of member to do the reenactment. They use solid members to do it, to try to throw, what's his name on their best, MCM. Again, I think MCM should come forward and sue. They should sue FIG for sure. This is engineering, and this is FIG's fault for telling them to process forward. And you should also sue VSL for their post-tensioning, because they consider themselves experts in structural repairs. They should know that this would not be the result. You would not repair this first. And yet I think somebody asked, should you epoxy it first? Or that's ridiculous. This turns out this chamfer, I believe, was added in a later stage. I don't believe it's connected at this time. So there's your long split of that member that they say they can push off 12. And yet they lack logic, because this is a space, this is a gap. It's the raising of it, the two of them going two different ways. The separation of it going two different ways. Let's see. There's your elevation. This explains why it's not down. They have it as spalling magically doing whatever they want it to do. It magically does whatever it wants to do. It heals itself and is able to push 11 off and raise 10,000 pounds into the sky, which can only be done by a hinge effect. I now, going over this over and over again, I can now explain the rubber band, why this is like this. This, again, 300,000 pounds of force. It breaks to the back of that little blister that's in the back of the diaphragm. It blasts through that little bit of, the force is released because they try to put that back together. But there's only a little bit of concrete in front of that. It's when they're trying to put it back together. Remember the split? It's split apart. So now you're trying to pull it back together, pull it back together with that little bit of remaining concrete. Sort of like, imagine if I said, I have an idea. Let's put a plate inside, internal to this right now, and then let me see if I can drag this around the world with me. You say, maybe you can even pull it off, but you'd say pull it off literally off of here. But you would say it's going to break apart, man. You can't put 300,000 pounds of force in there. It's going to pull apart. It's only, 4 inches of concrete left. But they don't have the logic to see that you can't put 300,000 pounds of force on 4 inches of concrete that's and then say we're going to close a gap with it. You logically say, how can we close that gap with that? The forces are only going to be on that what's remaining bit that's connecting these systems together, plus the dead load of all this. You would clearly say you're going to break the leg out of underneath of that. And they broke the leg from underneath of it is what I'm saying, that this blast is not really a hinging effect, that it's the blast on the rebar, the post-tensioning being released at 300,000 plus pounds of force from that plate, blasting through that, and the concrete, just like an explosion, it blasts the concrete away. And that's why we're looking at here. We're literally looking at, explains the puff of smoke other people see and talk about. It literally was an explosive event there. Literally explosive event of the 300,000 pounds of force using plate, no dynamite, just using forces. A steel plate that was dimensions of 8 inches by 8 inches being released, blasting through that concrete. That caused a failure in this zone there. At that point, it had no more tieback. Remember, I consider this a tieback bridge structure now. And I guess I should have talked about that. Let me grab it for anybody coming into this video. So tieback bridge, and remember this video is to clean up the other video, and I'll probably have about a third video. I think I'll have it pretty much, should have it all cleaned up as far as any stumbles I might have stated. The tieback bridge, you can look up Google here, and you can find out what tieback. I call them tieback bridges, the tied arch bridges, and this is a tied arch. I'm considering a tied back bridge because it's not quite an arch. So let's go from there. So what happens is, I got to start from scratch again for newcomers. Do you see there's no abutment here for the forces to be pushed out? And this is not an abutment enough, this steel. So what happens is the steel is connected to the longitudinal steel here, this bottom steel. And that's the lower deck, so we'll discount that. It's not connected to the lower deck directly. You see where it connects right there? This is where your tie backing is going. So the forces are trying to push out here, but it's connected to the steel. It then tries to push the steel away. Oh, but it's connected to the steel here, all connected. So the steel is in tension as it tries to push the loads. As these loads try to pull down on this structure, it tries to push the end outwards. It can't do it because it has to make the steel elongate, and it can't do it. So this stays stable until at such time it doesn't, such as rust, etc. Now let's just take away, I think I did this in the other video, remove these bars and leave one bar in there. And now push down on, why did I say that? If you attempt to try to lower this deck, that's the load of the weight, say an 80,000 pound tractor tries to push down on it. It won't deflect because the loads transfer up to the steel, of course with the truss members too, helping out. Transfers back into the canopy, into the arch, trying to pull it down. Again, it has the same effect of pushing back here, and then it's like a round robin, and it's back in the tension again. I don't know how large the scale of this, how much this truss system can carry, how much it's participating, but it's participating. It's creating some rigidity, and also it's a lot of the loads get transferred back down this truss member. It's not for free. Some of it will go back down these columns, these piers here. So it's not all just going back up in here and coming out to here from the bottom deck. A lot of it transfers right to here. But out to here, let's call it, some of that deflection, if I were to cut all these cables, we would see how much deflection would happen. This would fall down into the river, as we saw in the Taiwan bridge collapse. You need these cables, these hangers, to help transfer the loads out to this tie-backed area. It's the tied arch bridge, tie-back. So let's get to our structure. So while at this, so the structure is, the top of it is being pushed over, remember, over and up. And this gives us this beautiful stair step crack like you see here. And on this side symmetrically. And also the pattern here as the forces broke away and up. And that's why you don't have the bars. You have some kinking here in it, some bending in the bar there. These bars took a ride down the wall. These bars right here, they were sticking out all the time. It should be noted that you see the plastic, it's not rubbing against the wall. These are standing proud, standing strongly up. This explains why you also, my video explains why you see this in such good condition. All these bars are not bent, pushed away, as the NTSB and OSHA report states. Pushing away, you'd have these engrossment of concrete. You got to you have to push these bars, you're bending these bars, pushing them away, but clearly they look like they're 90 degrees facing us, not bent away. My explosive moment makes it justifies how you can get this though, that at 300,000 pounds of force exploding through this little bit of concrete that it has to finish off. And it's not much concrete it has to finish off. It's already got that crack, and it's only on an angle. It's not much at all. This is a fib. It's not been sheared. It's been cut by a torch, reported by the NTSB report. These bars in both NTSB and OSHA report, they remove them per engineering specifications and testing, whatever, you can remove them. And in real life, they remove them in their formula too, yet they're encapsulating this in concrete. They can't move. They can't move. You didn't move through them. This is number 11, showing still embedded. That's right. Number 11 still embedded. And this is my point I'm making. If you could add, like, keep adding more forces to this, you only have to cause this little bit of failure to happen, to blast through there. But it can't happen unless it's already mostly failed. That concrete back there was mostly failed, as we saw in the fine crack on 2.8. The structure was already leaning downwards. It already broke its bond. So the grip, and I was going to do future videos on this, the grip of the concrete takes place around all of this, all of the bar, and the concrete locks on it. So imagine a smooth bar, and you hold your hand on it. Now imagine that you're the concrete, and you grab hold of this stuff. It creates a heck of a grip. It's a pull-out force, they call it, and that's times all of these. This was really not designed for pull-out force because it was going to. They didn't really think of it that way. Probably more force towards us. Okay? And this is sort of indicated with the steel in there. This is the part that was installed first, and they were waiting for the concrete to be poured on the second part of the deck going up with number 12. The second part of the number 12, rather. It's not part of the deck. The second part of number 12 would be the pouring of the column part of it. It was poured at a plumb on purpose, I think, because to make it look plumb because of the 1% pitch they had on the structure. So again, my explosive technique explains why all the steel is in such great condition, and that explains that. Now let's pausing, and I'll grab it for you. So let's consider this the tendons, the post-tension from this is the failed end down here, and let's consider this now. This is how the load is transferring out to this deck equally with these transfer cables, tendons. And these are longitudinal cables. They're times 6 on each side. This will be A, B, C, D, 1 rather. 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. This is where, on this end, where if this was the hinge, its sagging has been reported way before this, and they didn't relate the sagging to the crack in the back over here at this point. The sagging takes place. The sagging takes place means these longitudinal cables are not keeping this thing taut, as I told you, keeping it flat. The rubber band has now dipped down. The consequence of dipping the rubber band down is all these are also interactive. It also pulls them down. If you get sagging here, we get pulling down. Oh, it's ready. I got to pause, guys. Oh. So where I'm at here is sagging's not for free. If you sag this deck, these are from the drawings, 2017 stamp. It's not for free. If you can pull this down at any degree, you're also going to be pulling down and react. You're going to have reactions everywhere. Down here, we see the pulling down of this, and this has post-tension in the canopy. When you pull, if I were to just pull this down, if I could just lower this part, so imagine me being able to pull this down, and that creates a hinge here, doesn't it? So this point, if I'm pulling this down only, it creates a hinge here. It's sort of a lifting effect, also a pulling effect on this one. Oh, which also has a pulling effect on this one, which makes it lean inwards. Also makes it go upwards. Same thing here. If I pull down right here, down into the ground, don't imagine you're not pulling in this direction. You're pulling down. My gravity levers, it's going down. I state it's equilibrium. The weight of the structure makes it go straight down. Well, it goes down the path. So it goes down this way as it's pulling downwards. So you've got a straight arrow coming down here, pulling downwards. Same effect. It's pulling down. This would be stable here, more rigid. It's not going to hinge as much, right? It's going to be a hinge. So these pushing down creates a hinge pushing this one up a little bit, just a little bit of diaphragm action going on there. But the same thing happens here. You're going to pull down. This will want to pull down also. Well, it would be connected here. So it'd want to create more force inside here, wouldn't it? And as the canopy part, same thing as the other end, as this is pushing down, it's going to try to lift this up. It's going to react at the points it's connected at. So it'll be reacting here and reacting here. And since this post-tension in the canopy is pretty substantial, when it tries to pull down, it holds this joint together. We don't find photographs of this joint breaking apart before the collapse. We have nothing of this joint breaking apart. So it raises this up to that degree. And that's that simple. When I say that degree, we're talking that fine crack. That fine, this is sagging. It now does this. We've got this elevation change. It's already up just by that much. But remember, the post-tensioning is still in place. Is not still in place. It is in place from the original post-tensioning. And number 11 is present and down number and the connection of back of 12 here. So it's in 11. So it's in the deck and also the back of 12. When I say that for clarity, let's look at this. See what I'm talking about here? The bottom A, and I call that top one B. This is A. It's totally in this deck. The deck goes all the way out to here. This is not showing the blister clearly, but that little dot, 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 you're in the blister right out here. So when you see that crack on the other side, that's indicating of the sagging because we have the report now from the NTSB stating that the crack, why is the bridge cracking? And he also had that crack that they photographed on 2.8. This is before the transporters were on there, but after they removed the scaffolding. A significant amount of scaffolding, some is down here, some is down here, some is down here. Some of the scaffolding are down here, supporting each one. Obviously can't hold it up in the air without them. So this is what it looks like in their rendering. This is that post-tensioning I talk about to you. So this is the part that stayed, and this is the part that's gone. That's the explosive effect, and that's how you get this all blasting out. I want you to take note. This is the deck. Follow the deck over. I did this in another video. There's only a little, and you follow this downwards. This only clips into bottom of 12, because if that's 12 above it, remember 12 is sitting on top of the deck. This is not 12. This is part of the deck diaphragm, this piece of blister sticking off. So even though you may think it's, oh, that's 12. No, there's a cold joint right here. I'm sorry, follow the deck across. There's a cold joint right there. That cold joint never seems to fail because the rebar's in here too, standing proudly in here. They remove it for their rendering. This is also where they're stating that number 11, all crushed up and cracked up and destroyed, has the ability to push 12 off the deck. It's just illogical thinking, and I know one of the guys has a PhD. It's just, as somebody commented, I forget who it was, he gave me a nice donation, appreciate it. He made a comment, and I pinned it. It was, he triggered me because he actually used my amygdala theory, that because you make this conclusive file, you don't want it, it's hard to change. Our egos are involved. Instead of going, yeah, that makes sense. It makes more sense. So if our two stories are presented, which would make more sense? My story or their story? My story automatically, even if I make mistakes, makes more sense because I'm not telling you to remove things, and I'm not telling you this broken up member is going to now kick this off. Their story is just ridiculous. That's OSHA, NTSB, and I don't know about any other periodicals that print and support that theory. And that includes Engineering Report, all the engineering magazines, every last one that reports that nonsense. Now let's talk about the tie-back bridge. So this was acting, great. Okay, so much for that, bounced me to the front. So this was acting as a tie-back bridge, not an arch bridge, tie-back. So the thing was sagging. At the point it was sagging is then telling you that, hey, you didn't do these longitudinal cables correctly. It should not be sagging in your system. I mean, who would design sagging in a concrete system? There's no room for the concrete to move. It's going to be, compressive, but now you put your canopy in tension because it's going to now have an arch in it. And then you also put this in an arch. So you lost if it's sagging, you've put both of them because they're connected together. You put both of them in tension. They're both trying to get back on top of here. You're stretching them. So if they're both supposed to be compressive, the whole system's supposed to be compressive. The moment you get sagging, you lost your compressive moment. You can't have your cake and eat it too. I can't show you a limp rubber band and say it's in compression. You're like, no, that's not in compression or anything like that. You're like, no. So it no longer was in compression at that point. It was all being held up by tension of the post-tensioning. And the profile was whatever the sagging was. The profile is no longer flat anymore. Now it's sort of an anchoring mode. That is, I'm going to exaggerate. So here's the post-tensioning going this way and back up like a huge smile. The anchoring is done at the ends at that point, each one of the diaphragms. So I did that exaggeratingly, so it helps you understand it. So now what's holding it up is the anchor, the diaphragm. It's no longer being held up by a straight, flat bar, piece of steel, as they would try to describe as an I-beam. It's no longer an I-beam. You don't have sagging I-beams like that. So now it's got this new profile that's now acting as anchoring. They're kind of pulling it back up now. They're no longer acting in compression. They're now pulling this, trying to get rid of this sag. Each end is now acting as a pulling action, trying to lift up the sag. But it has the weight it's always trying to overcome. And part of that interlocking of helping it out, helping it hold this thing together at that point now, is the interaction of all the diagonals, because they act as an anchor now, the tie-back system into each one of the diaphragms. That rebar, the post-tensioning bars in there. So what happens if I just remove one of these? Let's just take this out, because that's what happened. Once I remove one of these, we no longer have the anchor, the tie-back system, as I told you how it works. So what's the next point of if this is just removed, all fractured up? The next point is number 10. Number 10 now takes the load because it didn't fail yet. Your stages are, if this fails, what happens next? It's not spontaneous. It is some delay in there, millionths of a second, whatever it may be. But once this fails, the loads will go down 10 at that point because this doesn't exist. This structure will still try to carry the loads out to the diaphragm. Once it's down 10, the bridge does try to hold up just for that split moment until we see a break here and here, because this concrete and that post-tensioning, the longitudinal cables and specifically here, can't hold the loads of all of this canopy and the deck itself. Why do I say specifically this? Before I used to talk about what came first, the chicken or the egg. The deck broke first or the canopy broke first. I got that backwards. The canopy broke first or the deck. Now I state that the deck broke first, at the time of failure, and then the canopy broke second. But before that, before the deck broke first, the canopy was already failed because it was no longer, it had a flexural moment in it. It was sagging, and number 12 was lifting up in the air. It was up in the air per the images here. That this side is higher than this side. This side is higher than, if I were to take a thousandth of a ruler, a shim, I would butt against this and he would say, oh, that's higher. Why is it higher? It was equal concrete. How did it get higher in height? Remember, this is compressive still. It's still being under compression because the deck is sagging. And what happened is this anchor, the anchor in the back of this diaphragm was holding this bridge together. That cracking we see is from the bottom up, and then it hinged. It probably has 2 cracks in it that I can't distinguish at this point because I don't have more data. But that was holding this thing from sagging down, this anchor point back here, and it couldn't do it. And it overlooked, the sagging pulled it down. So let's get to the pulling down image. So as this was coming down, it pulled, this was coming down, it's sagging from here, pulling down, it raises this up. This is where we get our break here. Hey, thanks a lot. Thank you. I'm going to try to hurry this video up for you. Let me pause and come back to you. So the sagging of the deck and all this being locked in with these post-tension bars stopped any slide friction happening here because we don't see any photographs, evidence, or anyone reporting such. As it's creeping down, as this is creeping down, and I'm going to use accelerated creep or whatever version you like to do it, because it's slowly going to the ground. It's trying to establish equilibrium, so I'm trying to use the word creeping. That might offend some engineers here. So as it's hunching down, and I like the word creep because I want you to understand it's moving. It's actively moving, so it's accelerated creep. So it's going down, and then you can see the development of the cracks expressing how much it's sagging downwards. They have it acting as an individual moment down here, just individually able to elongate and push itself off. That's my whole issue, is that how can, even if you compress this times 2, how can it push itself off? Because it has to go cut itself in half because the bars are in the way. But they have it, the forces are created by this compressive force, and then also acting as a sliding effect. They have the bridge structure flat. All of them do. That would be NTSB and OSHA. Everybody, as far as I know, have it as flat. Not counting that sagging taking place changes the profile in all the interactions that are going on. That if this is sagging, this is no longer pushing there. It could be acting as a hinge and hinge effect. And for clarity, I no longer stand on the position that it hinged it off, pried it off, because I have now the 2.8 photograph. The 2.8 photograph, this whole crack changes is a game changer. This is the game changer for me. This is elevation from before while I was under post-tensioning. The sagging is now clear to me. The sagging is going on. So I have it just, literally as the photographs, explaining all the photographs, it's lifting off, the explosive effect, once they post-tensioning it, finishing off that little bit of concrete that would have been so easy to finish off because it's so fractured. It's so fractured. That it can push right through. It's so fractured. We're looking at the side column at that point, right? That this is so fractured that it's nothing for it. It explains why you have the gaps, the separation. Because one's moving and the other one's not, as it's trying to interact. It explains the gap here. The deck is sagging so much that it has a reveal here. This explains why. Also, that it's because it became loose, it now made the rotation counterclockwise. That for looking at the back end, counterclockwise, and this gets you your rotation where you're able to get tape measure sliding down sideways in there. It's kind of simple to me that way. I just see it so simply now, and now because it all ties in. I don't think anything's left off. I could probably pick at a couple of. I could probably pick at myself with the. Was it the initial crack? I'm going to leave it alone for now on that statement. So then we have this dropping down. Once the explosive forces of the 600,000 pounds of force in here, specifically though, not this one, 11A, but this one by itself, smashing through, finishing off the rest of this diaphragm, the little bit of diaphragm blister, releasing this last bit of anchor point. Because remember, this is a tie-back arch structure, or tie-back bridge is what I'm saying. This is the tie-back. It's freestanding. They, on the other hand, think of it more as freestanding because of post-tensioning in it. Because of the sagging, I say it's post-tensioning along the longitudinal post-tensioning is a failure, and now it's acting as a tie-back structure. But the failure started before they moved the structure. So this is all engineering failure and not anything else. That this on 2.8 is my smoking gun. The 2.8 and the sagging of the structure. The statement sagging of the structure, it explains everything. Explains all the cracks, both sides, sagging of the structure, and what's really going on, the tie-back bridge structure. That this was acting as anchor points. Once you release those anchor points, you get the bridge to be able to. So you release this through the explosive action, you get it to be able to punch down and fall down. By their theory, 12. So most engineers, which I had told me number 12 is a zero force member. Well, if it's a zero force member, we can get rid of it, can't we? If your theory, we can just throw it in the trash can. So no harm, no foul. So what? 12 is lost. Yeah, 12 is very important in the capacity of sorry guys, I haven't eaten and I'm grabbing a little food as I'm trying to round up this video. So 12 is in the capacity of this. It was an anchor. This was part of the anchor point. It was the anchor point. And I'm going to terminate the video. I think you guys following it. I guess I should have read more of my comments from that I wrote back to Mark. I got to do this now to find Mark's comments. You see, I got to do multiple stages to find comments now. And okay, he wrote me back, but I won't read you, Mark. Let me read this. Oh, so don't, just because, always be willing to change with the data. And I've always showed you guys that. Once the data comes, I'll change it. So what I changed here is that we don't have a hinge effect of prying 12 off. We have an explosive effect. And that's because now the crack explains itself. That 2/8 crack gives me a different path. And I don't need the hinging effect. I have the explosive effect right in front of me all along. You guys can come here and read this. I'll pause it. To be clear, I'm just trying to amend it. It's the explosive effect of the post-tensioning. Let's see if I missed anything here. It's a tie-back bridge system, not the tied arch system, but like a tied-back arch bridge system. And Mark, let's give Mark a little hit here. All right, I'm not going to finish reading. Let me right now. Let me go ahead and terminate the video and load this up for you guys.